Evaluating limits analytically. So there's different techniques you can use to analyze limits. We have direct substitution, factoring, and rationalizing. So I'll do an example of each one. Direct substitution is nice. You simply plug in and you can find the limit. So here's an example. The limit as x approaches 2 of 4x to the third plus 3. And this is called direct substitution. So because this is a polynomial function, there's no breaks in the graph. Another way of saying that is that it's a continuous function. You can simply plug the 2 in and calculate it, and that'll find the limit. So in this case, if we plug 2 into this function, 2 to the third power equals 8. 4 times 8 is 32. 32 plus 3 is 35. So the limit is 35, which means as x approaches 2, y approaches 35. Not only does it approach 35, it is 35. So in other words, f of 2 is 35. So it's the actual point exists. The existence of the point doesn't matter because limits are what is it approaching. So as x approaches 2, y gets closer and closer and closer to being 35. That's a limit. It doesn't have to be 35 at that point. In this case, it is because it's a continuous function. So all polynomial functions are continuous like that with no breaks in the graph. The same thing goes for trig functions. All trig functions are continuous. So for example, if I took the limit as x approaches pi over 2 of the sine of x, I know that the sine function is continuous. There are no breaks in the graph. So I could simply do direct substitution and just plug in pi over 2, and the sine of pi over 2 is 1. All right, let's just take a quick look at that. So here's a sine wave, and this is pi over 2 right here. Is that 1? And I can see that as x approaches, as x gets closer and closer to being pi over 2, y gets closer and closer to being 1. And in fact, it is 1. So another way of saying that would be that f of pi over 2 is 1. So it actually, not only is it approaching, but it is 1. So that's called direct substitution. And it's nice because when you're doing direct substitution, you just have to plug the x value into the function, and it gives you the limit. It gives you the actual value, which is the limit. Okay, let's look at a couple other techniques, factoring and rationalizing. A little more work involved here. So this is number 3. The limit as x approaches 3 of x squared plus x minus 12 over x minus 3. And so the first thing we try is direct substitution. So we'll plug the 3 into this function and see what we get. And so that's 3 squared is 9, plus 12, plus 3 is 12, minus 12 is 0, over 3 minus 3, which is 0. So we get this 0 over 0, which is called the indeterminate form. Indeterminate form, 0 over 0, which means we can't determine what the limit is, at least at the moment. But we can do something to this function. We can sort of reduce it and then take the limit. So we'll factor the numerator. X minus 3. And we know that 3 times 4 is 12. And 4 minus 3 is 1. We're trying to get this 1 here. And then, of course, we can reduce this. And so we're taking the limit as x approaches 3 of this new function, which is just x plus 4. And now I can do direct substitution. 3 plus 4 is 7, so the limit is 7. So what this looks like when you graph it, now that you've reduced it, you end up with just a linear function, x plus 4. So the y-intercept is 4 and has a slope of 1. So it looks like this. And as x approaches 3, y approaches 7. But it's actually it's actually a hole. I should have made it as a hole. It's actually a hole in the graph at 7. It's a big hole, but it's approaching 7 because in the original function you couldn't plug 3 in. Right? It looked like it was going to be an asymptote, but once you reduced it, it's what we call removable discontinuity. So it looks like an asymptote, but once you factor it and you cancel, you couldn't plug in 3, but now you can plug in 3. So we call that a hole, and you end up with a linear function once it's reduced. So you have a linear function with a hole in it. So as x approaches 3, y approaches 7. It gets closer and closer to being 7. And you would see that if you made a table here of values just before 3 and just after 3, and you would notice that you were getting closer and closer to 7. It will never reach it in this function. It will reach it in its reduced form. So we call that a hole. Okay. I hope that was clear. And that's factoring. And now we just have one left, that's rationalizing. And you can rationalize a numerator or a denominator. It doesn't matter which one. It depends on the case. So here's a limit as x approaches 0 of the function x plus 1 square root minus 1 over x. And you can see that if you try direct substitution, which is what you should always try first, you end up with 0 plus 1, which is 1, and the square root of 1 is 1, minus 1 is 0 over 0. So you end up with the indeterminate form 0 over 0. And when that happens, that usually means that something else can be done to the function. So let's rationalize this. And you rationalize by multiplying by 1. And 1 can be written in many different forms. So in this case, I'm going to use what's called the conjugate. So it's the opposite of this. Instead of doing minus, I'm going to make it plus. So it's x plus 1 over square root of x plus 1 plus 1. And you can see it's the same expression over itself, so it equals 1. So I'm multiplying by 1, which means I'm not actually changing the original function. And this is called the conjugate because what's going to happen here when you FOIL, if you will, the middle term will just sort of disappear because you'll have a negative of this and a positive of this, and they'll cancel each other out. So when you multiply this out, this radical times this radical will make the radicals disappear, and you'll just end up with x plus 1. Again, when you're doing FOIL, this and this will cancel each other out, and then you just have negative 1 times positive 1, which is negative 1. So, and you can work that out on scrap just so you can see it, but that's what you get in the numerator. At the bottom, I would just leave it like this for now, x times x plus 1 plus 1. Okay, and now I'm going to come down another line here. This numerator, obviously these two cancel each other out. You end up with x over x times x plus 1 plus 1. And of course the x's cancel, and you end up with 1 over x plus 1 plus 1. And we have to remember that we're taking a limit. So going back to the original problem, the limit as x approaches 0. And really I should write that over and over again each step so I don't forget when I get to the end that I'm actually taking a limit. Now I can do direct substitution, and if I plug in 0 here, I get 0 plus 1, which is 1. Square root of 1 is 1. 1 plus 1 is 2. So the final answer is 1/2. Which means that if you were to graph this on Desmos, this original function, you would see that as x gets closer and closer to 0, the y value is getting closer and closer to being 1/2. It doesn't actually get there, but it approaches it. And it's probably worth looking at this on Desmos. So that's called rationalizing. Again, I rationalize, in this case, I rationalize the numerator. Sometimes you need to rationalize the denominator. If this were upside down, we would have done it from the perspective of the denominator. But either way, that's called rationalizing.